Hi everyone, this is Mr. Zarzik, and in this screencast I'm going to discuss the operation of ammeters and voltmeters in circuits, as well as how these devices are designed to both read correctly and not affect the circuit in which they're inserted. So let's get started. We've seen that there's two basic types of circuits that we build more complex circuits out of, and that's the series and parallel. In series circuits, the voltages are just the sum of the voltage drop across any circuit component, so in this case 3 resistors. The total current is a constant throughout because there's only one path for the current to follow, and that the total resistance can be found just by taking the sum of the individual resistors. Parallel circuits operate a little bit differently in that the voltage across each pathway is a constant, and if there's just the one battery, those voltage drops are equal to the voltage provided by the battery. The total current splits among the different pathways, and those individual pieces of the current can be added together to get the total current, and that for resistance we use this special equation where it's the 1 over the total resistance is equal to 1 over each of the individual resistors summed up. So 1 over RT is equal to 1 over R1 plus 1 over R2, and so forth. The rules for these two types of circuits really dictate both how we connect and how we design an ammeter and a voltmeter. So let's take a look at how each are connected and how each are designed. An ammeter measures the current flowing through a circuit, and so in order for it to read the current in a circuit properly, it must be wired in series. So for example, in this circuit with 3 series, I'm just going to call this resistor right here R1 just for talking points. If I wanted to measure the current flowing into or coming out of this resistor, I'd have to put the ammeter in series. And so what I would physically do is I would take and I would break the circuit and I would insert the ammeter in series with the circuit so that any current that's flowing out of the battery has to flow through the ammeter before flowing into the resistor. Likewise, I could also take and wire in the ammeter right here. I could wire it in right after the resistor because the deal is that any current flowing into the resistor is going to be equal to the current flowing out of the resistor. For this case of the simple series circuit, the current is constant throughout, so as long as I wire that ammeter in series, I'm going to get the correct current reading for R1 regardless of where I put it. All right, now that's just the case for series circuits. As far as their design goes, we want the ammeter to have as little effect on the circuit as possible. And so when we design the ammeter, we make it to have as close to zero resistance as possible. If you think about the ammeter as just another circuit component, say like a resistor, okay, well, if I add in any kind of significant resistance value here, well, that would change the total resistance of the circuit, because in a series circuit we just add up the resistors, so any resistance of the ammeter is going to get added into that total resistance. And so the trick is that we want to make the resistance of the ammeter as close to zero as possible, and so that when the circuit operates, it's almost like it doesn't even know that the ammeter is even there. So the ammeter is equivalent to an extremely small resistor, again as close to zero as possible. A voltmeter, on the other hand, gets wired in parallel. It gets wired in across circuit components. And so if I wanted to draw that in for this circuit, if I wanted to measure the voltage across this resistor here on the right, I would connect it in parallel across it. So this would be to measure the voltage for, I'll call this one R2. If I wanted to measure the voltage across R1, okay, well, if I'm clever and I understand the operation of parallel circuits, well, then I know that the voltage across this entire chunk of wire that I've highlighted in green is all the same. And likewise, the voltage across this chunk of wire that I've highlighted in yellow is also across the same. So technically speaking, I could be reading the voltage for either R1 or for R2. So here's my R1, and the way that I've connected the voltmeter here in parallel would read the same voltage for both. Now, if you're not comfortable with that just yet, I'll show what the voltmeter would look like wired in parallel across R1. So it would just be like this. Okay, and if I did this, I'd get the exact same volt reading as I did for R2. Notice that the 2 leads of the voltmeter, one of them goes to where I've highlighted in yellow, and one of them goes to where I've highlighted in green. If I go back to my original drawing here of the voltmeter wired in parallel across what I called R2, Okay, you see that one lead goes to where the green is, one goes to where the yellow is. And so what the voltmeter is really doing is it's measuring the change in voltage, the voltage drop across either of the two resistors, R2 or R1. So now that I've talked about how we wire in a voltmeter, let's talk about how we design a voltmeter to have as little effect on the circuit as possible. Since voltmeters get wired in parallel, one way to think about a voltmeter is almost like you're adding a whole nother resistor here just in parallel. So how do we make that extra resistor have almost no effect upon the circuit? Well, we need to keep as little current as possible from going through the voltmeter, which is equivalent to this extra little resistor. So if I think of the total current flowing out of the battery like this, okay, well, it's going to split up between R1, R2, okay, and then whatever current flows through what I've drawn as a resistor, but is really just the voltmeter down here. So how do I minimize this? Okay, well, the ways we can think about it is Ohm's Law just says V equals IR, and given that by attaching the voltmeter in this fashion, what we're really doing is making it part of these two conductive paths. So the bottom lead here becomes part of this yellow part of the circuit, and so all of this is along one voltage, and the other lead of the voltmeter becomes part of this part of the circuit, which is all just one conductive path and one voltage here. All right, so the deal is that there's a voltage drop across the voltmeter, which is equivalent to the voltage drop across R1 or R2. So thinking about this in terms of Ohm's Law, if I want to keep this I as small as possible, what I want to do is make the resistance of the voltmeter as big as possible. See, the thing is that the voltage across the resistor is already dictated by the battery and the way I've wired up the circuit. So the bigger I can make the resistance, the smaller the current will be that will actually flow through the voltmeter. Okay, and so I'm just going to go ahead and write out the equation for calculating the total resistance of a parallel arrangement. And so I'm going to call this 1 over RT for the total resistance is 1 over R1 plus 1 over R2. That's the circuit without the voltmeter. Okay, if I call this the resistance of the voltmeter, so I'll call this RVM for voltmeter. If I added this in like this, I want this term over here to be as close to 0 as possible, which means that I want to make the resistance value of the voltmeter as large as possible. The bigger the denominator in the fraction, the closer this becomes to 0. So if I could think of the voltmeter as having near infinite resistance, that means that that's like saying that in this equation, this term shrinks to effectively to 0, in which case there is no effect on the total resistance of the circuit. So again, I want to design my voltmeter with as much resistance as possible to minimize the current flowing through it. That will allow it to have almost no effect whatsoever on the circuit. Okay, so just so you can see what it looks like, in this series circuit, I've already got my ammeter inserted in series. Okay, remember that the ammeter has almost no resistance whatsoever, so it will have essentially no effect on the operation of the circuit. It won't affect the equivalent resistance or the current flowing through any of the resistors. For the voltmeter, I connect the voltmeter in parallel, so if I was going to draw that into my diagram, okay, if I wanted to measure the voltage across this resistor right here, I just insert my voltmeter like that, and that would measure the voltage across this resistor. Maybe this is R2, and this is R1, and we'll call that R3. If I wanted to add other voltmeters in, this would be the voltage across R1, and then this is how I would show the voltmeter wired in parallel across R3. Okay, so now how do I wire in an ammeter in series in a parallel circuit? Okay, well, to do that, it's a little easier for me to zoom in over here. Okay, the deal is that the ammeter must be wired in series. And so for this first resistor, I'm going to call this one R1, and I'll call this one R2 just for talking points. If I want to measure the current flowing into R1, I'm actually going to take and I'm going to put the ammeter right here in the circuit. See, now there's only one wire going into R1, and then there's one wire coming out of the ammeter back into the rest of the circuit. I could also put the ammeter over here. Okay, and this would measure the current flowing out of the resistor. But remember, from conservation of charge, whatever current flows into the resistor is the current flowing out of the resistor. As far as R2 goes, okay, if I want to wire that in, okay, I would wire that in just like this. I would show it right here. Now, I know this is a little confusing, okay, because we've got this voltmeter here. But remember, this voltmeter has really, really high resistance so that it measures passively. Almost none of the current that's flowing here is going to take this branch over here for the voltmeter, okay? And so we can just think of the voltmeters as things that passively measure. They don't change the operation of the circuit. So I could put the ammeter from R2 right here. I could also take and put the ammeter in the circuit over here. Okay, and that would also measure the current coming out of R2. Again, that voltmeter can be a little bit confusing there. All right, so I don't want to leave you with that. So what I'm going to do instead is just take and draw the ammeter over here coming out of R1 and say, all right, well, that's going to measure whatever current is flowing through resistor number 1. Okay, the one thing that we do need to watch out for, okay, is if I put the ammeter over here, okay, well then this would be measuring the total current in the circuit. The split of the current doesn't happen until we get over here. All right, and so again, this is how I put the ammeter to measure the current flowing through R1, and this is where I would need to put the ammeter to measure the total current flowing through the circuit. So just to quickly summarize, ammeters which measure current are wired in series, and when they're built with almost zero resistance, zero internal resistance. Voltmeters, which are there to measure voltage, are wired in parallel, and when they're built with as large resistance values as possible. This is Mr. Zarzak saying thanks for watching, and I'll see you in class.